Hello ladies and gentlemen. In this video we will conclude chapter 3 where we will analyze different kinds of circuits, starting with the rectifier circuits, which forms an essential building block of the DC power supplies. The first form of the rectifier circuits that we will discuss is the half-wave rectifier. Okay, so the half-wave rectifier is as follows: Vi with a diode in series with a resistance. We already analyzed this circuit before, but I guess with the ideal diodes. Now we will discuss the non-ideal diode case. Okay. Now we need to draw or to sketch the waveform and the transfer characteristic. In order to do that, we need first to start with the reference. Let's draw the reference time with respect to V input, and as a sketch, the peak values are Vi and minus Vi. Okay? Then we have to mention the two cases. The two cases are if Vi is positive and if Vi is negative. Okay? Now it's not quite right to say if Vi is positive and Vi is negative. For example, in this case, let's say that Vd operates at 0.7. Okay? Now, when will the diode work? When Vi is greater than 0.7. Vi greater than 0.7, and it will be off or reverse bias when Vi is less than 0.7. So it's not actually right to say positive or negative, but these numbers, these constant numbers, actually it depends on the position of the diode and the number of diodes. So to simplify things, there are always two cases: when some Vi is greater than something and it's less than something. So in order to simplify things, we will say that the first thing is it's positive, and the other case is when Vi is negative. Okay, this will simplify things. Let's continue. So if Vi is positive, the current is moving clockwise. Hence, the diode is on. If the diode is on, then it will be replaced with a voltage source. So the circuit will be like this: positive, negative, Vi, a voltage source, okay, and a resistance. This is the output, okay, and the voltage source is the DC source, the DC diode source is 0.7. So what is the output? The output is VO positive minus VO negative, which means this point minus this point. Okay, this point is 0 because it's grounded, it's always 0, and this point we need to think of it. Now if this point is 0, okay, and this is Vi, so 0 plus Vi is Vi. Okay, if this is Vi, the sign that is furthest from you is minus, so Vi minus 0.7 is Vi minus 0.7. So this point is Vi minus 0.7. Okay, Vi minus 0.7 minus 0. So the answer is Vi minus 0.7. Now, if Vi is negative, the current will flow in the opposite direction, and the diode is off. When the diode is off, it will be represented as an open circuit. Vi open circuit, and then R. Okay, this is the output. Now we need to find V output again. V output is equal to VO plus minus VO minus. VO positive is this point and VO negative is this point. The negative side is 0 because it's grounded, and the positive side is still 0 because there is no current due to the open circuit. Hence the resistance is no longer there. Okay, as if it's no longer there. It's like a short circuit. So the voltage at this point is similar to this point, so it's 0. Okay, let's draw now the waveform. Time V output. Okay, I recommend that the first thing that you do in sketching is plotting the V input or the reference as a dotted line, okay, with peak values Vi and minus Vi. Now for V output, if Vi is positive, then the output is Vi minus 0.7. Vi minus 0.7. Vi minus 0.7. It's here. Okay. Now, as this is an AC signal, we need to draw a new signal. Okay. If it was DC, then we have to crop. If Vi is negative, V output is 0. So this is the answer. Now it's correct that there should be shifting here. For example, the right graphing should be like this. If this is the reference, okay, then the most accurate solution is that you need to shift it a little bit like this, okay, and then draw it. But this shifting, we will not consider it in this course to simplify things, okay? But just keep it in mind. Now, let's continue. Now we do the waveform with a peak value of Vi minus 0.7, okay? For the transfer characteristic, it's VO with respect to V input. When Vi is positive, V output is Vi minus 0.7. Now let's say that V output is Vi without the minus, then it will be a diagonal line, correct? But now there's some shifting to minus 0.7. So we need to shift the diagonal line 0.7 like this, okay? If Vi is negative, then V output is 0. So it will be a horizontal line on the x-axis, okay? So this is the waveform and the transfer characteristic. Before moving on, now I said when we're drawing the waveform, we need to check whether the signal is AC or DC. In this example, it was AC. How did I know it's an AC? Because it consists of a Vi component. Vi is AC, okay? Let me give you a hint of when do we get DC signals. We get DC signals. First, what will happen if we're drawing an AC signal? If we are drawing an AC signal, then we need to draw a new sine wave. Sine wave. It doesn't have to be a sine wave, it depends on the input. If the input is, for example, sinusoidal, then you have to draw a sinusoidal. If it was a square wave, then the output will be a square wave. Anyhow, but the main idea is that it has to be new, okay? If we are drawing a DC signal, then we need to crop we need to crop the peak value. I will show you what do I mean later on. Okay, value. Okay, now when do we get a DC signal? You get a DC signal whenever you have such circuits. Okay, for example, if you are drawing V output across a DC source, then you have a DC output. Okay, or for example, if you have such a circuit, then again you are drawing some of the it's either one part or the two parts are DC. Okay, this is VI and the other side is grounded, for example, or has a value, for example. Okay, so whenever you see such circuits, I will explain them later. We need to crop. Okay, moving on. Now, in selecting diodes for rectifier designs, two important parameters must be specified: the current the diode is expected to conduct and the peak inverse voltage, PIV, that the diode must be able to withstand without breakdown, determined by the largest reverse voltage that is expected to appear across the diode. So PIV. Each rectifier circuit has a certain PIV, and PIV is the peak inverse voltage. Let me write it down. Peak inverse voltage okay. Each diode has its own peak inverse voltage. In this circuit, the half-wave rectifier, we have only one diode, so we will have only one PIV for the diode, which is V input. So whatever the peak value of VI is, this is the PIV of that diode. Okay. Now there's a way to calculate the PIV, but it's fine to memorize it. Moving on to the second type of rectifier, which is the full wave rectifier. Full wave rectifier. It looks like this. This is actually a transformer. I don't know why does it look like this, but consider it as a transformer. The full wave rectifier has two diodes, one resistance, and it's grounded from here. Okay. Now there are two voltage sources. VI. Great. V output is measured on the resistance. This is D1 and this is D2. Okay. This is the transformer again. There are two types of transformers, step up and step down, just as a side note. Okay. Now we need to analyze it. In order to start, we need to draw the reference of the input. As we do not have numbers, we will assume that the peak value is VI and the negative peak value is minus VI. Okay. Let's write down the two cases if VI is positive, if VI is negative. Let's see what will happen if VI is positive. If VI is positive, the current will flow clockwise. Okay, it will split here due to the junction. Hence, D1 is on and D2 is off. Let's redraw the circuit. This is a voltage source. This is an open circuit. Here is our resistance. This is grounded. Okay, V output. Those are our sources, input sources. This is 0.7. Now, if this is grounded, then this point is VI, because here it's 0 plus VI, hence you will get a VI. If this point is VI, the sign that is furthest from you is minus, so it's minus 0.7, hence this point is VI minus 0.7. This point is the same, VI minus 0.7. Now what is this point? This point is actually minus VI, minus VI. This point is 0. The sign that is furthest from you is negative, so you will get a minus VI here. Okay? So what's V output now? V output is the positive terminal minus the negative terminal. Hence, it will be VI minus 0.7 minus 0. So it's VI minus 0.7. Okay? Now, if VI is negative, let's pick another color, green, dark green. If VI is negative, the current is flowing the opposite direction. It will split here. Okay, hence D2 is on and D1 is off. Let's redraw the circuit. Okay. Now, what's V output? Let's start analyzing it. This point is grounded. This point is VI because of the sign. And this point is minus VI again because of the sign. Now, the value of the voltage source is 0.7. Hence, this point is minus VI minus 0.7. This point is the same. Okay. So V output is VO positive minus VO negative. VO positive is minus VI minus 0.7 and the negative terminal is 0. Hence the answer is minus VI minus 0.7. Factoring out the minus, you will end up with VI plus 0.7. Okay, this will help in sketching the curves. Now, the waveform. Time V output. Let's first put the reference. Okay. Now, as you can notice here that both the outputs, they consist of VI, hence AC. They are AC signals. Okay. So we need to draw a new signal. The peak values are VI and minus VI. If VI is positive, then the output is VI minus 0.7. The output is VI minus 0.7. So it will be here VI minus 0.7. And for the negative case, this is VI minus 0.7. Let me write it again, VI minus 0.7. Okay. Now for the other case, it will be, look, if Vi is negative, then it's this side, right? Then it's this side. This is Vi negative. Okay. Now, it's Vi plus 0.7, so it will be a little bit shifted upwards. But then we have this negative sign, so it has to be flipped. So it will be like this. That's why it's called a full wave rectifier. Both sides of the wave are on the positive. Okay, let's draw the transfer characteristic. If Vi is positive, then the output is Vi minus 0.7, which is shifted to 0.7 like this. And if Vi is negative, let's see. Let's only say that V output is only Vi, so it will be like this, right? But then we have a Vi plus 0.7, so we need to shift it to minus 0.7 like this. But because of the minus, then it has to be flipped. So the final answer will be minus 0.7 like this. And you have to connect them so it becomes continuous. Okay? Now, the last part is the PIV. Here in the full wave rectifier, we have two PIVs. Why? Because there are two diodes. What are the PIVs? PIV for D1 and PIV for D2. Here we have two sources, so the PIV will be 2Vi minus the other diode. For example, here we are having D1, then it will be 2Vi minus VD2. Here it's VD2, then it will be minus VD1. Okay? Moving on. Another implementation of the full wave rectifier is a bridge rectifier. Bridge rectifier. Let's analyze it. How does the bridge rectifier look like? It's like this. It consists of 4 diodes. It looks nasty. Okay, this is D1, this is D3, this is D4, and this is D2. Okay, let's start sketching the curves. So we will begin by drawing the reference. Time, V input, peak values Vi and minus Vi. Okay, then we will say if Vi is positive and if Vi is negative. If Vi is positive, the current will flow like this, it will split. Now D1 is on, D4, actually D4 is in the opposite direction. I have made a mistake here. It's like this. Okay, now D4 is what? D4 is off. Let's continue. So if it's off, then this is an open circuit. The current will not continue from this direction. It will not continue here because it's off. Okay, So the only current that will continue is from through D1, and then it will split again. D3 is off, hence no current will flow in this direction. Current will only continue like this, and it will go down. Remember, this became open circuit, so current will not flow in the opposite direction. Okay. So it will continue like this, and it will not flow in this direction because D3 already became off. Okay. So D2 is on. Let's redraw the circuit. It will look like this. Voltage source, open circuit, a resistor with V output. This is another voltage source. This is open circuit. Okay. This is VI and V output. The values here are 0.7 and 0.7. Okay. Now, what's V output in this case? This is grounded, hence this point is VI, then this point is VI minus 0.7. Okay. If this is 0, then this value is 0.7, because 0 plus 0.7 is 0.7. So V output is VO positive minus VO negative. VO positive is VI minus 0.7, and the negative value is 0.7. Hence the output will be VI minus 1.4. Okay. Doing the other case, the current is flowing in the opposite direction. D2 is off, hence open circuit. The current will not flow from this channel. Current will only continue from here. So D2 is off. D3 is on. Okay. Current will flow in this direction and this direction. Hence D1 is off and D4 is on. Okay. This D1 became off, so no current will flow across it. So D2, D4 is off. On. Okay, let's redraw the circuit. This is open circuit. This is a voltage source, resistance R, VO, voltage source, and this is an open circuit again. My circuits are awful. Okay. I'm messing it up. Okay, it has to be like this. This is VI and this is V output, and these numbers are 0.7. Now, what's V output? Let's begin. This is 0, hence this point is VI. If this is VI, then this is VI plus 0.7, and this point is minus 0.7. Because this is 0, the sign further from you is minus, hence minus 0.7. So V output is VO positive minus VO negative. VO positive is minus 0.7, and the negative value is VI minus 0.7. Hence, it will be minus VI minus 1.4. Minus VI plus 1.4. And now it's time to sketch the waveform and the transfer characteristic. V output, reference, VI minus VI. Okay, V input is sorry, Vi is positive, then the V output is Vi minus 1.4, so it will be like this. Vi minus 1.4. Okay, if Vi is negative, then it will be Vi, then we have a plus 1.4 and then a minus, right? So it will be flipped like this. So the answer in the negative side is let's pick a color that we did not pick, so it will be like this. Okay, it's very similar to the full wave rectifier, but here in the bridge there are two diodes working at the same time, whereas in the full wave rectifier there's only one diode. Now, transfer characteristic. If Vi is positive, then V output will be Vi minus 1.4, and if Vi is negative, then the output will be Vi plus 1.4, and it's flipped, so it will be like this: Vi plus 1.4. Sorry, it's not like this, right? Or it is like this? No, it's not like this. We have to put only the numbers actually. Let me redraw it again. So here, if Vi is positive, let's consider only Vi. So it will be like this, right? But then we have to shift it 1.4 units. So it will be like this. This is the correct diagram. And if Vi is negative, Vi will be like this. We need to shift it to the negative side by minus 1.4 and then flip it. Okay, so it will be like this, and then we connect them. Now, before moving on, we need to mention the PIVs. In the bridge rectifier there are 4 diodes, hence there are 4 PIVs, one for each diode. PIV for D1, PIV for D2, PIV for D3, and for D4. Bridge rectifier consists of only one input voltage source minus the diode. Which diode? The diode that is vertically under or above it. For example, for D1, which diode is vertically below or above it? It's D3. So PIV will be Vi minus VD3. For D2, it will be D4, vertically above or under it. So it will be VD4. It can be easily memorized. For D3, it will be D1. And lastly, for D4, it will be D2. Okay? Simple. Moving on, we are done with the rectifiers. The next type of circuit that we're going to, actually there's still a rectifier, which is the peak rectifier. Let's discuss the peak rectifier. As its name suggests, it identifies your peak value. How does it do it? Let me show you. It's a Vi, source, diode, and a capacitor. Okay? V output is measured on the capacitor. Now, we will consider the ideal case of the capacitor. Ideal case of capacitor, not the diode. The diode is ideal. Ideal case of capacitor and ideal case of the diode. Ideal diode. Okay? How will this kind of circuit operate? Or how will it behave? So here we're having VI with respect to time. Peak values are VI and minus VI. Okay. Now, let me draw the waveform. Time with V output. Plotting the reference. VI minus VI. Now here, the source is flowing in the positive and negative direction. It's going upwards to the positive peak and then downwards to the negative peak. The job of the capacitor is to charge itself. So when the voltage is in the positive term, in the positive side, or it's increasing, then the capacitor will charge. The current is flowing this direction, the capacitor is charging. So it keeps charging until it becomes fully charged. Once it becomes fully charged, okay, now VI will continue. It will decrease again. When VI reaches its peak value, it will decrease again, right? Now when it decreases again, the voltage across the capacitor is higher than the voltage of V input, because now the voltage of the capacitor is at the peak value and VI has decreased. So the actual current will be in the opposite direction, right? So what will happen to the diode? It will turn off. Hence, when VI is decreasing, the voltage across the capacitor will stay as is, because as it's ideal. Now, when VI is at the peak value again, nothing will happen. VI, the voltage of VI is the same as the voltage across the capacitor. Then when VI decreases again, the voltage of the capacitor is still higher than VI, so V output will still stay the same. Hence, peak rectifier. I hope it's clear. Moving on. Now we will take the peak rectifier again, but with the non-ideal case of the capacitor. Okay, peak rectifier again. We're having ideal diode and non-ideal capacitor. Non-ideal capacitor means it will not keep its voltage forever. It will lose energy with time. So the circuit will be like this. We have a voltage source, VI, diode, capacitor, resistance R, V output. Okay. Now, time with V input, VI and minus VI. Let's draw the output waveform. VI as a dotted line first. Okay. Now, initially, the capacitor is zero charged. Okay, it has no energy. When VI starts increasing, the capacitor will keep charging until it becomes fully charged. Once it becomes fully charged, okay, VI will decrease again. When VI decreases, then the voltage across the capacitor will be higher than the voltage across higher than VI, because VI is now decreasing. Okay, hence the diode will be off. When the diode is off, then the circuit will be like this. Capacitor and a resistance. So as if now you're having two different circuits. VI that is going up, increasing and decreasing by itself. And now who is stealing from the capacitor? The resistance. The resistance is stealing from the capacitor using Ohm's law fashion. So whenever the circuit disconnects or the diode is off, the resistance start discharging the capacitor through Ohm's law in an Ohm's law fashion. Now when at the same time VI will be decreasing and increasing again. Once VI, the voltage across VI, is higher than the voltage across V output, the diode will connect again. Hence the capacitor will be charging again until it becomes at the peak value. At that moment, VI will start decreasing again. Once it decreases, once it drops below the peak value, then the diode will be off. When the diode is off, then the resistance will be consuming energy of the capacitor, hence the voltage across the capacitor will decrease. Okay? Once VI becomes higher than the voltage across the capacitor, the diode is on and they reconnect, capacitor charges again. Okay? So this how the behavior of the circuit will be. Moving on to the next part, which is the limiter circuits. As its name suggests, it limits the output voltage. Limiter circuits. We will consider different types of limiter circuits. Let's begin with this one. We have a resistance, a diode. Okay, this is VI, this is V output. Let's say that VI is 5 and minus 5. VI is 5 volt. VD is 0.7 volt. VZ is 8 volt. Now, as we have numbers for VD and VZ, then it's directly non-ideal. Whenever you have a VD or VZ, then it's directly a non-ideal diode. When you do not have numbers for VD or VZ, now you have to doubt, is it ideal or non-ideal? You need more information. Like someone has to tell you whether it's ideal or non-ideal. Okay? Let's start analyzing this circuit. So if VI is positive, if VI is negative. If VI is positive, the diode will act, actually it will be on, hence there will be a voltage source of VD equal to 0.7. So V output is what? V output is actually VD, which is 0.7. Remember, is this a DC or an AC signal? This is DC. Why? Because you're measuring V output across a DC source. As I mentioned here, that there are two cases for DC. One of the two, two cases only. Those are two cases, and this is one of the cases has been satisfied, where V output is across a DC voltage source. Okay. The other case, if VI is negative, hence the current is flowing in the opposite direction. Now, whenever the current is flowing in the opposite direction, we are used to say that the diode will be off. However, in this case, we need to check, is it really off or it's in the breakdown region? Because if you remember this curve from the previous videos, in the reverse or in the negative or in the other side, in the opposite side, there are two cases. There's the reverse, there's the off case, and there's the breakdown case. Okay. However, in the forward bias, there's only one scenario, which is the forward bias. That's why we do not check. Whereas in the opposite, we have to check, is it really off or breakdown? How do you know if it's off or breakdown? We need to compare VI with VZ. This is VZ. Okay. We have placed negative because it's already in the negative side of the axis. So VZ is minus 8. What's VI? What's the range of VI? The range of VI is from 5 to 5. So it's from 5 to minus 5. Did the negative side exceed the Zener, the threshold for Zener? No, it's here. Hence, the diode is off. If the value of VI exceeded VZ, where it's here in this region, then we have a breakdown region rather than off. Okay, we will take the other case. So here it's off rather than a breakdown. Now you might wonder, why did I check now in this example for off and breakdown? In all the previous videos and the previous examples, I only said it's off. The reason why is because now we have a VZ. We have been provided with a value for VZ. Whenever you have a value for VZ, then you have to check whether the diode is really open circuit or it's in the breakdown region. If it's in the breakdown region, I will tell you later what will happen. So what's V output in this case? V output here, it's VI. Because there's no current, hence the resistance is useless. This is VI. So V output is equal to VI. Okay. Let's plot the waveform and the transfer characteristic. Here VI is 5 and minus 5. If VI is positive, then the output is 0.7, and because it's DC, we have to crop the sign, the wave. Okay, so here it's 0.7, and in the negative side it will be VI. It's AC, hence it's a signal, a new signal. Okay, simple. If VI is, now let's draw the transfer characteristic. V output across V input. If VI is positive, then we have a 0.7. Whenever you have a number, you need to put the number on both the x-axis and the y-axis. Reason being, when will the diode be on? The diode will be on only if VI is greater than 0.7. That's why we have a 0.7 here. And what is V output? It will be 0.7. That's why we have V output 0.7 at the y-axis. So here it's a DC value, constant value. And if VI is negative, V output is equal to VI. It's a straight line, and we need to connect it. So it becomes a continuous curve. It's going through the origin. Okay? Let's take another example. Say this is part B, R, diode, V output. VI is 10 volt, VD is 0.7 volt, VZ is 8 volts. Okay? Reference. Minus 10. Now let's say if VI is positive, if VI is negative. If VI is positive, the diode is in the opposite direction of the diode, so we need to check, because we have been provided with VZ, if it's really off or breakdown. Okay, so this is the IV characteristic. This is minus Vz, which is minus 8. Vi is minus 10 in the reverse direction, so it's actually breakdown. If we are in the breakdown, then the diode will be converted to a Zener. Zener in the same direction as the diode. It will be like this. So this is the positive terminal and the negative terminal of the Zener. And as the current is flowing in this direction, then the Zener will be on. So here we're having a resistance and then Zener with positive here and negative here. Okay. So this is V output. Vz is 8. So V output is 8 volt. Now if Vi is negative, the current is flowing in the opposite direction, hence the diode is on. Here it's breakdown. So it will be negative positive because the positive terminal is at the bottom and the value is 0.7, value of Vd. This is V output. So V output here is 0.7. Plotting the waveform and the transfer characteristic. Now notice that both numbers are constants, hence DC, both of them. Okay, so Vi, we said it's 10 and minus 10. When Vi is positive, V output is 8 DC value, so we're cropping. And when Vi is negative, V output is 0.7. I think it's minus 0.7, right? I have made a mistake here. Yes, it's minus 0.7 because they are in the opposite direction of the output. Okay. Transfer characteristic. V output with V input. If Vi is positive, then we're having 8 and 8 constant. And in the negative, it's minus 0.7, minus 0.7, constant value, and then you connect them. Simple. Moving on. Part C. Let's take this example. Vi is 5 volt, Vd is 0.7, Vz is 8 volt. This is the reference. 5 and minus 5. If Vi is positive, we need to check whether the diode is off or breakdown. Z is minus 8 and Vi is minus 5. It did not cross the breakdown region, hence it's off, open circuit. So redrawing the circuit with the new design. V output is equal to V input. If Vi is negative, the diode is on, hence it's in the it's like this because here's the positive and this is negative. Okay, 0.7 V output. V output is minus 0.7 volt. Drawing the waveform and the VTC, voltage transfer characteristic. This is the reference, 5 and minus 5. Minus 5. If Vi is positive, then V output is Vi, this is AC, new signal, and if Vi is negative, then it's minus 0.7, okay? V output with respect to V input. If Vi is positive, then actually it's better to start with the numbers, with the DC values. This is AC. So if Vi is negative, then it's minus 0.7, minus 0.7, minus 0.7, straight line, and then Vi to be like this, okay? Moving on. This is part C, then part D. D1, D2, this is V output, okay? No numbers. So Vi is what? It's a general reference. Vi with minus Vi. If Vi is positive, if Vi is negative, if Vi is positive, the diode is on, D1 is on, D2 is off. Now here it's off, it's not breakdown. Why? Because we were not given Vz, a value for Vz. And here we're having 0.7, this is open, okay? So the output is equal to 0.7 volt, okay? If Vi is negative, then D2 is on and D1 is off. This is positive and this is negative, 0.7 V output. So V output is minus 0.7 volt, okay? Let's draw the waveform. V output, this is the reference, Vi and minus Vi. If Vi is positive, then the output is DC 0.7, and if Vi is negative, then it's minus 0.7, also DC. So this is the graph, okay? For the transfer characteristic, if Vi is positive, then it's 0.7, and if it's negative, it's minus 0.7. So the graph will look like this, going through the origin. It's like this. Anyhow, it should be a straight line. You got the point. Okay. Moving on. Let's draw the reference. If Vi is positive and if Vi is negative. If Vi is positive, the light is on. Hence, V output is what? V output is actually this is 0, then this is 5 volt, okay, 5 plus 0.7 is 5.7. So V output is 5.7 minus 0, so it's 5.7 volt, okay, 5.7 volt. If Vi is negative, then the diode is off, okay. Now in this case, what's V output? Let's take it step by step. This is 0. If this is 0, this point is Vi. There is no current, hence resistance is useless. Then this point is Vi. Now you might say, why isn't this point 5 volt? How can it be 5 volt? This point is actually 5 volt. Okay. How will 5 volt jump to this point? There's an open circuit. Okay. Sorry. No. So V output in this case is VO plus minus VO minus. So it will be VI minus 0. So it's VI. If I asked you what is the voltage drop between this point and this point, let's call it VY, then it will be VY positive minus VY negative. VY positive is VI and VY negative is 5. So this will be the answer. Okay. That's just a side note. Let's now plot the V output in its waveform and VTC. Time V output. This is our wave reference. VI with minus VI. Okay. If VI is positive, we have a 5.7 DC value, cropping, and if VI is negative, then it's minus VI. For VTC, VO and V input, okay. If VI is positive, it's 5.7, and if VI is negative, then it's VI, straight line. Okay, moving on. Part F. Let me drink some water. Now we are going to take a case where there's a Zener diode. Let's take these numbers. VZ1 is 7 volt, VD1 is 0.7 volt, VZ2 is 8 volt, and VZ2 is 0.8 volt. VD2, sorry. VD2. Okay. Now, the reference as usual, time V input, VI and minus VI. We will say if VI is positive and if VI is negative. If VI is positive, the current is flowing clockwise. Z1 is off because of the polarities, and Z2 is on. Z2 is on. Whenever a Zener is off, it gets converted to a diode in the same direction. So it will be like this. Here's positive and here's negative, and as the current is flowing clockwise, then the diode will be on. So it looks like this. This is R. This is our diode VD1, and this is our Zener VZ2. So the output VD1 is 0.7 and VZ2 is 8. So the output will be, let's take step by step. This is 0, positive, hence this is 8. If this is 8, the sign that is furthest from us is positive, so it will be 8.7. So the output is 8.7 minus 0, 8.7 volt. If Vi is negative, then the current is flowing in the opposite direction. Hence, Z2 is off, so it will be converted to a D2 diode, and Z1 is on. Okay, let's now draw it. This will be a zener where negative is up and negative is upwards and the positive is downwards, and the diode of D2 will be in the same direction as Z2, so positive is downwards and negative is upwards. So here we are having D2, which is equal to 0.8. This is VZ1, which is 7 volt. So the output will be, let's see, this is 0. The sign that is furthest from us is minus, so it's minus 0.8. Then we're having minus again, minus 7, so it will be minus 0.8 minus 7, hence minus 7.8 volt. Let's now draw it. V output with time and V output with V input. Here we're putting the reference, Vi and minus Vi. Okay. If Vi is positive, then the output is 8.7. It's DC, so we are cropping. And if Vi is negative, it's minus 7.8. We're cropping again. Here we are assuming that Vi is greater than V output. For example, Vi, let's say Vi is 20. So here it's 20 and minus 20. Okay. For VTC, it will be 8.7, and minus 7.8, minus 7.8. Okay. Usually in Zener, it's not a straight line, it's curvy line. Anyhow, you can put it as a straight line for simplification. It depends on your instructor. Now, the last idea in sketching is the clamped capacitors. Clamped capacitors. Clamped capacitors. Okay. Let's say here we have Vi, capacitor, and a diode. Now, if you compare this with the peak rectifier, the capacitor and the diode are actually swapped. Okay, here we're considering the ideal case. Ideal case. In such circuits, okay, you have to do shifting upwards or downwards. It depends on the shape of the direction of the diode. If the diode is facing upwards, let me write it as a note. If diode is facing upwards, then we need to shift upwards. Okay, so now we need to shift upwards, but to which point? The lowest point of the curve, on the curve, towards on the curve, has to be the point, the voltage point under the diode. Let's call it Vx. So where's Vx here? It's here. under the diode, Vx. What's the point of Vx? It's actually 0. Now, usually you're given first a reference, so which you can shift V input. Okay, let's say the curve is like this. It's -6 to 4, a square wave. Okay, so what's V output? V output will be, now as we said, this diode is facing upwards, so we have to shift upwards. Till which point? Till the lowest point is Vx, which is 0. So we need to shift upwards so that the lowest point, this lowest point, becomes 0. So the curve, the output curve will be like this. Okay, it has to be exactly the same. I don't know why this side is fatter, but it's just by coincidence. It has to be exactly the same, only shifting. Okay, now let's label the axis. This point is 0. If this point is 0, this has to be 10. Why? Because the amplitude here, the amplitude of this curve is 10. Hence, the amplitude here has to be 10. And if we started from 0, then the maximum point is 10. Okay? Now, let's take another. That's only for ideal case, by the way. If we had non-ideal case, okay, if the diode was non-ideal, then we need to start from Vx. We need to start at Vx, let's say Vx plus 0.7. okay, so we need to add 0.7 first. So instead of 0, let's consider this as non-ideal, then you need to start from 0 plus 0.7. So you need to start here. If you start here, then you have to end at 10.7. Let's take another example. Vi capacitor and the diode is facing downwards. This is grounded. Okay, so here we have to shift downwards. If the diode is facing downwards, then we need to shift downwards. And the maximum or the highest point has to be the voltage point under the diode. Let's call it again Vx. So where's Vx here? It's here and it's equal to 0. We need to be given the reference in order to draw the V output. So Vi with time, let's say it's the same as the previous example, -6 and 4. So V output will be as follows. Time with V output, we are shifting downwards this time, and the maximum point has to be equal to Vx, which is equal to 0. So we need to start, so the curve will be like this. Okay, this has to be -10, this is 0. The amplitude here is 10. If the amplitude here is 10, then the amplitude here has to be 10 also, and that's why I have written -10. Okay, now if the diode was non-ideal, then we need to shift then we need to start at Vx minus 0.7. Okay, I hope it's clear. It's simple, just shifting upwards and downwards. And for shifting upwards, the lowest point has to be the voltage point under the diode, whereas in the shifting downwards, the highest point has to be the point under the diode. Now, before concluding this video and this chapter, let's take one more example. Okay, let's take one more example on the limiter circuits actually. Let me first write down the question. Here it's 15, 1 milliampere, 1 kilo ohm, D1, another diode D2. Okay, this is grounded and this is VI. We need to plot V output. Okay, now how do we start? We start by drawing the reference. Then we say if VI is positive, if VI is negative. Okay, let's put a value here, 10, so it becomes more tricky. Actually, this question is a bit tricky. We need to think of it, so be careful. Now, if VI is positive, VI is positive, how is the current flowing? Is it flowing outside VI or going into VI? Let's redraw. Let's take another form which you are used to. Now, if VI is positive, VI is flowing out of VI, right? Hence, the current is flowing in this direction. So is D1 on or off? D1 is off. Okay, so this became open circuit. No longer exists. This is 15 volt and this is 10. So that's the high potential and low potential. Hence D2 is on. Let's redraw the circuit. It will be like this. We have here 15 volt, voltage source 1 milliampere, a resistance R, which is 1 kilo ohm, and a short circuit connected to voltage source 10. This is open circuit, which is VI. Okay, so now how do we find the output? The output is equal to simply Ohm's law. I is equal to V naught minus 10 over 1K. V naught is equal to 10 plus 1K multiplied by 1 milli, which is equal to 11 volt. Now notice that this number is actually DC. Why? Because VI is actually disconnected from the circuit. It's no longer connected, and it's just simply a number. There's no VI component in it. Okay? Now, taking the other case, if VI is negative. If VI is negative, which is smaller, negative or 10? Of course, it's negative, right? VI is negative, meaning it has negative numbers or values less than 10. So all the current will flow to VI. So no current will flow through 10. Therefore, D2 is off and D2 is on. D1 is on, D2 is off. Okay? 15 volt. This is 1 milliampere. 1 kilo ohm, V output VI, and this is open circuit 10 volt. Okay, now how do you calculate V output? It's Ohm's law again, V naught minus VI divided by 1K. So V output is equal to it's equal to VI plus 1K multiplied by 1 milli. So it will be VI plus 1. Now I recommend that you do not substitute in values of VI. Usually you're given values for VI, for example 15 volt, or let's say 20. So you do not think that VI is 15 here, 20. Okay, my advice to you is to not substitute in numbers, because as soon as you plug in numbers, you will plug in 20 here, okay, and you will get 21. That's the first mistake. It has to be minus 20 because you are in the negative side. It has to be minus 20. And then when you plug in minus 20, even though you got the correct answer, but you will end up misdrawing the VTC or the waveform. You will think that it became a DC. Okay, so it's better to keep it in the VI form. Let's now draw the waveform. Time with V output, VI as a reference. Here we are having 20 and minus 20. If VI is positive, then V output is 11 and it's DC. So we have to crop. And in the negative, V output, it's VI plus 1. So it's VI plus 1. So it has to be like this, right? So it will be minus 19, and it's a new signal because it's AC. See, it's AC because there is VI component. Now, so this is the waveform. Let's draw now the VTC. VTC is a bit tricky in this example. I will show you why. You need to be careful. If VI is positive, the output is 11. What we usually do is we put 11 on both X and Y axis. Now in this example, it's different. Okay? The X axis is no longer 11. The X axis depends on the value facing VI. Depends on the value facing VI. Depends on this value. What is this value? It's 10. So what you have to do is you have to put 10 and then a straight line. Okay? Why 10? You remember at the beginning of this video I said that it's not necessary to be positive and negative. This is not accurate. What's really accurate is that it depends on the circuit. Now who's determining, what's the threshold that is determining which side is on? Actually it's 10 in this example, because if VI is greater than 10, then D1 is off and D2 is, no sorry, actually if VI is greater than 10, true, then D1 is off and D2 is on, because the current will flow directly to 10 as this is greater than 10. Whereas when VI is less than 10, then all the current will go to the negative, which I call the negative, but it's physically not negative. Okay? So here, what is more accurate is to say if VI is greater than 10 and VI is less than 10. Okay? Now, anyhow, just remember that in this example, when drawing the VTC, you need to be careful. You need to put the number that is facing VI, which is 10. Okay? Let's continue. Now, if VI is negative, V output is what? It's Vi plus 1. What does that mean? Vi in negative is like this, correct? Plus 1, it will be like this. But then you have to connect them. So it has to be the following. Let's reconnect them. So it has to be like this. Okay? Going through -1. Going through -1. I hope it's clear. I know it's confusing. The only trick is that you need to be careful of the X value when drawing the VTC of such circuits. Okay? It's a long video and I have given you a lot of examples. I know it's a little bit hectic, but with practice you can get used to it. Good luck. We have concluded chapter 3. Thank you.